All right, let's get started. Oh, let's not get started. Why is this not? Is there a different cable I should be using?
The projector might have turned itself off, so I just turned it on.
Oh, okay. Well, so maybe I'll start talking, but hopefully the projector will come on in a second. I think it's just booting up. Okay, so today we're going to talk about reframing control as an inference problem. But before we get into that, a few class announcements. So they'll come on the projector shortly, but I'll just say them out loud. First of all, homework 3 is due today at 11:59 p.m. So hopefully all of you have already started or even perhaps finished it by this point. The other point is that the peer reviews, oh, there it is. The peer reviews for your project proposals will be coming out shortly. So all of you would have completed the reviews by now, and we'll release them to all of you soon, and then you'll see what kind of feedback you're getting from your peers. Do make sure to take into account the feedback from the TAs and from the peer reviews. And if you have any questions or concerns, or you think that maybe you need to change your project proposal a little bit, just come to office hours, discuss that with the TAs. You're welcome to discuss that with me, and so on. And then homework 4 is going to come out tonight, and homework 4 is going to be on model-based reinforcement learning. Okay, today's lecture. So today we're going to talk about something a little different. We're not going to be talking so much about new RL algorithms, but more about a new framework for thinking about RL and decision-making problems. So we'll start with this question. Does reinforcement learning and optimal control provide a reasonable model for human behavior or animal behavior? Basically, you could think, well, maybe people are doing things with intention, people have goals. Reinforcement learning seems to be a framework for telling us how to take actions to achieve goals. So does reinforcement learning provide good predictions about how people might go about achieving goals? And if not, why, and is there a better explanation? Is there a model of behavior that is based on the similar principles to the ones we discussed in this class, but is better at explaining the kind of behavior that we see from humans and animals? And the main question we'll be concerned with in this lecture is, can we derive optimal control or reinforcement learning and planning as a probabilistic inference question? Can we work out a probabilistic framework that describes why some behaviors are more likely than others? This is a little bit different than what we've seen in reinforcement learning before, because in reinforcement learning so far we've seen a setting where you just want to find the best behavior, the one that maximizes reward. And we'll actually see that in some cases you might want to also reason about behaviors that do not optimally satisfy, that do not optimally maximize reward, but are still pretty good. And we'll see what pretty good actually means. And then this will actually not only allow us to model behavior of other agents, but it'll also actually lead to other reinforcement learning algorithms that are different from the ones we covered before that have some interesting properties. And we'll see that at the end of the lecture. And then next week, we'll actually build on the, not next week, this week on Friday. This week on Friday, we'll actually build on this theoretical foundation to devise what are called inverse reinforcement learning algorithms, which are algorithms that infer reward functions from observing behavior. So you watch somebody do something and you figure out what is the goal they're trying to accomplish, essentially by inverting the reinforcement learning framework. So that we'll see on Friday. So the goals for today will be to understand the connection between probabilistic inference and control, understand how specific RL algorithms can be instantiated in this framework, and understand why this might actually be a good idea, why we should actually study this. So let's start with the human behavior stuff. For quite a bit of time studying the the goals behind human behavior, the objective functions behind human behavior, has actually been something that a lot of people have been concerned with. This is some analysis of running gates from Edward Muybridge from the 19th century, where he was actually a pioneer in photography, but what he did is he recorded videos, or I guess what at the time was videos of people performing various physical activities, and used this to try to understand biomechanics. Today, there's quite a bit of research trying to analyze human behavior to try to figure out the goals and objective functions that underlie both low-level skills, like, how does a person choose how to walk from over here to over here? Will they take a straight path? Will they take a curvy path? What are the kind of terms that humans try to balance out when they decide how to act in goal-directed situations? Reaching behaviors are very often studied in this setting. If you ask a person to reach from one point to another, how will they do it? What is important for them, what is not? And also higher level behaviors. Like if you ask a taxi driver to navigate from one location to the other, how do they prioritize all the different terms that might come up in their objective function, so to speak, to decide on the best route? And if we can understand these kinds of things, then we can also build predictive models. We can make predictions and say that, well, in these situations, people will do this. In these situations, they will do that. Could be super useful in lots of application areas. If you have an autonomous car, for example, that can reason about people's goals, it can watch pedestrians, it can figure out that this pedestrian is probably going to cross the street based on what it infers about their goal, whereas this other one might not. So it's a topic of scientific study, and also one with a lot of relevance in applications. So one thing we might say is, well, we learned a lot about computational frameworks for optimal decision-making in this course. It seems like humans are pretty smart. Perhaps humans are doing something rational, at least sometimes. So perhaps those computational frameworks can be used to make predictions about what people will do if we believe that they're acting mostly rationally. So then we could say, well, maybe we assume roughly that a person, when they're choosing which actions to take, solves a problem that looks kind of like this. Maybe they're trying to maximize their reward subject to a constraint that the next state will be governed by the dynamics. Or the same thing in probabilistic land. Perhaps they're trying to maximize their expected reward, where the expectation is taken under the system dynamics and their stochastic policy. And then we could say, well, if we've seen some human behavior, if we've seen people actually taking actions, perhaps we can figure out what their R is that best explains the actions they actually took, and that'll tell us what their goal might be. So we can actually do some experiments on this. These kinds of experiments are more often done with monkeys than with humans, but you can do them with humans too. So you can have a monkey do some task that involves, let's say, reaching a location, a very simple motor control task. So the monkey is holding a little joystick, it's controlling a little dot on a screen, the dot starts off over here, the monkey's goal is to bring it over here, and you say, well, what will my rational monkey do? If people aren't rational, maybe at least monkeys are rational. Perhaps the monkey will take a straight line path, because that is indeed the optimal path to the goal for most reasonable reward functions that reward the monkey for reaching the goal. But then you take this setup, you put in the monkey, and you have the monkey do this stuff. And maybe the monkey is actually a very smart monkey, and it does the task well, but it executes paths that look like this. Right? So they reach the goal, the monkey gets the reward for reaching the goal, but they're not really the shortest path. They're not the ideal optimal path. So you might say, well, is there something wrong with my monkey? Like, is it perhaps, for some reason, not truly optimal? Like, why would the monkey do this? And maybe the explanation is that the monkey is actually, it's pretty good at doing this thing. It's just an approximately optimal monkey. Approximately optimal in the sense that it mostly does the right thing, but when the stakes are low, when the stakes don't matter, the monkey gets lazy. Humans get lazy too. So the monkey will achieve the goal, but it will do so in kind of in a sloppy way, because it doesn't, it gets the same reward if it reaches the goal either way. So if it makes a little mistake here in the middle, it kind of just doesn't matter. But what does that really mean from a computational standpoint? What does it mean that it doesn't matter? Well, it means that the monkey's behavior is stochastic, meaning that there's some randomness to its behavior, but its behavior is not totally random. It's still going to reach the goal because it wants the reward for reaching the goal, but in between, it might do some random things, especially when those things don't affect its ability to achieve its goal. And this is something that we have not seen yet in conventional reinforcement learning. Conventional reinforcement learning doesn't say anything about some rewards matter more than others. Conventional reinforcement learning just says, do the optimal thing, do the straight line path. So how can we explain these curvy paths, the sloppiness and these mistakes? We can say that good behavior is still the most likely. You know, all things being equal, on average, things will reach the goal and they'll kind of be centered around this shortest path. But behaviors that are suboptimal can still occur with some probability, especially if the reduction in reward is low. So the best path is the most likely, but paths where the reward is a little bit lower can still occur with reasonable probability. And this might get us a decent model of our suboptimal monkey. So how do we deal with probabilities in machine learning? Well, we need to set up a model of our system. We need to set up a probabilistic model. So instead of saying that the monkey will always take the argmax, we'll have to write down some equations that describe the probabilities of the different actions that the monkey might take. So if we want to talk about probabilities, we should start by working out a probabilistic model. And a good starting point for our probabilistic model is to begin with what we know. So we know that for MDPs, they have states and they have actions, and states and actions relate to each other based on a particular model. So they have the Markov property, which means that S2, condition on S2, S3 is independent of S1, and you have this system dynamics, which is the P of ST plus 1 given ST-AT. So we can start with that. That gives us some kind of starting point. P of S prime given S comma A. And then we can write down a probability for a trajectory, for a sequence of states and actions. And we'll call this P of tau. Now this by itself is not actually super interesting, because saying, well, what's the probability of an action, of a trajectory occurring through like random actions in my MDP, that's not really a model of what the monkey is doing. The monkey is not just taking random actions, it is actually trying to achieve the goal. So this particular thing is not quite enough. We need to add something to this model to explain why the monkey might actually choose the actions that are more likely to reach the goal. So we need to add another variable to explain near optimal or approximately optimal behavior. So here, if we just write down P of tau, there are no assumptions of optimal behavior. So what we can do is we can add these variables that I'm going to call optimality variables. And this is going to be our evidence. Remember, in a probabilistic inference problem, the evidence is what you know. So what do we know about the monkey? Well, we know that the monkey is trying to reach that goal, and it's doing so approximately optimally. So in the general case, we'll formalize this knowledge as observation of optimality variables, which I'm going to say for now are going to be binary variables. And I'll define them shortly. So we'll just say these optimality variables are binary variables. They're either true or false. Either the monkey is trying to do something or it's not doing anything. It's just doing random stuff. And if we know the monkey is trying to reach that goal location, we know that all these variables are true because we know that it is indeed attempting to reach its goal. And then the way that we're going to encode that goal is by choosing an appropriate distribution for P of OT given ST-AT. And then when we want to actually figure out what is the distribution over possible trajectories we might see, then our probabilistic inference problem is to figure out P of tau given the evidence, which is O1 through capital T. So what we're going to choose, and this is going to seem a little mysterious at first, but it'll actually become clearer shortly why we do this. We're going to choose P of OT given ST-AT to be proportional to the exponential of the reward function. And we'll see in a second why we do this. It turns out that the result actually ends up looking a lot like regular reinforcement learning with a little bit of stochasticity. So we're going to choose the probability of this binary variable to be proportional to the exponential of the reward at that time step. And now let's see what happens if we plug that into our probabilistic model. So if we want to figure out P of tau given O1 through T, we can just write down by definition of conditional probability that this is equal to the joint probability of the trajectory and all of the optimality variables divided by the probability of the optimality variables. And if we're concerned primarily with probabilities of trajectories, we can ignore the denominator up to a proportionality constant, and we can write this as being proportional to P of tau, which is the probability of tau happening just from the MDP without any notion of a goal, times the product of these optimality variables. The optimality variables are all independent of each other given the states and actions. So we can just multiply them in there, and we just say the probability of a trajectory given that you know the monkey is optimal is simply the product of the probability of the trajectory happening in the MDP randomly times the product of the optimality variables. Now the product of exponentials is equal to the exponential of a sum, which is where I get this right-hand side. And now things actually start to look a lot more reasonable. We have the probability of this trajectory is proportional to its probability of happening just through the random dynamics of the MDP times the exponential of its total reward. So if, for the sake of simplicity, we assume that maybe the dynamics are just deterministic. There's always one S prime that has a probability of 1 and all the rest have 0. If the dynamics are deterministic, this first term will always be a constant. And that just leaves the second term. And that makes a lot of sense. That just says the trajectory with the largest reward is the most likely. And then suboptimal trajectories can also happen, but their probability drops off exponentially as the reward gets worse and worse. And it turns out to be a fairly sensible model of this kind of suboptimal behavior. It says the monkey will usually do the right thing, and it will make mistakes, and the mistakes that it will make will be the ones that are going to reduce the reward by relatively small amounts, because trajectories become exponentially less likely as the reward becomes much worse than the optimum. So it's a simple model of near-optimal behavior. Question?
So this is the model of like some sort of like semi-optimal or like some kind of agent that's acting probabilistically?
Right, so this is a model for an agent that is attempting to achieve a goal, but not doing so perfectly. It's in some sense the simplest model of an agent that makes mistakes. So that basically will give you agents that execute these kind of blue paths rather than just always executing the black path. And of course, one of the things we might do with a model like this, which is what we'll see on Friday, is actually invert it and say, well, if you know the tau and you want to figure out the r, this will give you probabilities that you can use for that. Okay, so why is this kind of thing relevant to us? Well, we can model suboptimal behavior, so as I said, this will be important for inverse RL. We can also use this connection to apply inference algorithms to solve control and planning problems. So there are a lot of methods that have been developed for approximate inference in probabilistic models, and we can actually use some of those ideas to get better algorithms for reinforcement learning and control if we're prepared to accept this approximate optimality framework. And it also provides an explanation for why stochastic behavior might be preferred. So even though the model, as I motivated it, was really motivated from the standpoint of modeling agents that can make mistakes, in some cases you might actually want to use schemes like this because you might not want to greedily always do the thing that you think is optimal, perhaps because you want to get better exploration, or perhaps you want to make sure that your agent is robust to mistakes. So maybe you will intentionally train it with a model that allows for mistakes so that when at test time someone goes in and perturbs it, someone changes the environment a little bit or affects its ability to execute the actions it wants, it'll still be robust because it got used to making those mistakes and now it can recover from them. So there are a number of benefits to actually working with a framework like this. So let's go through some of the math for how we can actually go through this kind of probabilistic model and get back policies and value functions. So in this framework, planning or decision making amounts to solving an inference problem. Inference means you have some evidence and you want to figure out the posterior probability of some other variables given that evidence. And there are a number of questions that we can ask about a probabilistic model like this with this kind of optimality variable probability. So one thing we could ask is, how do we compute backward messages? How do we compute the probability of optimality from the current time step until the end, given a particular state in action? It turns out that if we can compute these backward messages, that can make it very easy for us to then compute a policy. And the policy in this model is a probability of an action given a state and given all of the optimality variables are true at all times. That makes sense. It's just what's the probability you'll take a certain action in a certain state given that you're attempting to reach your goal. And then a third question, which will turn out to be very important later on when we talk about inverse reinforcement learning, is how to compute forward messages. So forward messages answer the question, what is the probability that you will land in a state ST if you have been optimal up until this time? So forward messages essentially allow us to predict how likely we are to land in a state, and that can be very useful when we later on want to infer what is the reward function. So I'll go through each of these three questions, starting with the backward messages. So the backward messages, those of you that are familiar, by the way, with hidden Markov models and Kalman smoothing will recognize this pretty quickly. It's essentially the same math, just now with actions thrown in. So a backward message, which I'm going to call beta, that basically tells you what is the probability that the optimality variables are true from time step little t to the end, given your current state in action. And the nice thing about these backward messages is that you can compute them recursively, backwards through time, very much in the same way that we do dynamic programming. So how do we do this? Well, we just crunch through the probability theory. So we say, okay, we want probability of t through capital T given SDAT. That's equal to the probability of t through capital T, comma st plus 1 given SDAT, where we're integrating out the st plus 1, right? So you can always put in any variable and integrate it out. And now this thing you can actually factorize, because you know that, that the optimality variable at time step t is conditionally independent of st given st plus 1, right? Because the optimality variables depend on this thing. So this optimality variable is independent of this state given this state. So now you can actually pull out everything from time step t plus 1 until the end and make that only condition on state st plus 1. Because you know that everything from t plus 1 to the end is conditionally independent of state st given state st plus 1. So that's why here we just increment this by 1 and we omit all the st and at. Now if you want to get the st plus 1 on the right side, you need to then multiply in by the chain rule p of st plus 1. So we have now p of st plus 1 given stat. And this thing, this is just a factor in our graphical model. So we actually have a CPT in our model for p of st plus 1 given stat. And then this last bit, this is what's left over, p of ot given sdat. This is the only remaining optimality variable that is not independent of st. But this thing, that's just this thing up here. So we know p of ot given stat. So now we factorize this thing into three terms. The first term takes care of all the future optimality variables. The second term is our probability of transitioning into st plus 1. And the third term is just our probability of the optimality variable at time t, which is the exponential of our reward. So this term we know, this term we know, and that just leaves the first term. So the first term, let's analyze it a little bit more. For the first term, we can do the same trick. We can put in now the action, and we can express it condition on st plus 1 and at plus 1. And we have to integrate out the action, so we multiply that by p of at plus 1 given st plus 1. Now, why do we want to do this? Well, we want to do this so that this whole thing becomes recursive, because this term, probability of optimality of t plus 1 through capital T given st plus 1, at plus 1, this is exactly beta t plus 1. So if we can just figure out this thing, we will express everything in terms of terms that we know, which are the CBDs in the model, and beta t plus 1, which will allow us to compute all the betas recursively backwards in time. So this is going to be our beta at t plus 1. And this term, this is kind of an interesting term. This term says, what's the probability of an action given a state without making any assumptions about optimality? It's kind of a funny thing. Like, what's the probability that the monkey will do something given that the monkey is not trying to do anything in particular? We can choose this term. We can choose it to actually be anything we want, and we'll see what happens when we make interesting choices for that term. But for now, I'm going to claim, and I'm going to actually prove this to you later, but for now I'll just make this unsubstantiated claim, that without any loss of generality, you can ignore this thing. You can set it to be a uniform distribution, meaning that if you are not assuming that the monkey is trying to do anything, then all actions are equally likely. Once you know that the monkey is trying to do something, then not all actions will be equally likely. But if you don't know what it's doing, all actions are equally likely. And if you assume that it's a uniform distribution, then it just amounts to a constant, which means that we can ignore it in this analysis. So if we make this simplification, then what we see is that we can compute the betas recursively backwards through time by following the following rule. For time steps little t, starting at the second to last time step and ending at the first time step, first we calculate the backward message at time step t, which we do by multiplying the probability of the reward, that's this thing here in red, times the expectation with respect to the next state. So that's why we have the p of st plus 1. And what is the expectation of? It's the expectation of what I'm going to call the state backward message. So this is the state action backward message, and this is the state backward message. And the state backward message is simply defined as this thing down here. So it's the expectation with respect to the action of the state action message. So then our backward recursion just consists of computing the state action message by multiplying the exponential of the reward by the expectation of the next state message, and then computing the state message by taking the expectation with respect to the action. And then we just repeat this process until we get to time step 1. And at the very beginning of this process, at t equals big T, then there is no next state, so there the backward message is just exactly P of O capital T given ST AT. So that's easy. Does anyone have any questions about this recursive procedure for computing the backward messages?
So the term you omit, it's the policy of the monkey?
So this term, P of AT plus 1 given ST plus 1, is the probability that the monkey will take an action in a particular state when we don't assume anything about optimality. So the policy is AT given ST comma O1 through capital T. This is not the policy. This is a kind of a prior on the monkey's actions. So it's reasonable to assume that if the monkey is not trying to do anything in particular, it'll just do random stuff. And we'll see how we can actually change that later on. Question?
I'm not sure again how you get the B beta big T as big T, like the first one.
Yeah, let me write that out. So the question was about the beginning of the recursion. So at the beginning of the recursion, you have to compute this term, beta STAT. Now, if we look at the equation for this, beta STAT is going to be defined as the probability of O capital T given STAT. And fortunately, this is actually a CPD in our graphical model. So that's just that thing in the top right corner, evaluated at time step capital T. So the beginning of the recursion is actually very simple. Any other questions? Okay, let's continue. So let's take a closer look at this backwards pass. It looks different than what we've seen before. If you're familiar with hidden Markov models, this might look familiar, but it doesn't really look quite like a reinforcement learning procedure. But it turns out that there are a few small changes we can make that will get this thing looking very similar to reinforcement learning. So we're going to be a little suggestive in our notation. We're going to define the log of beta TST as V of ST. Just coincidentally, I'm going to call it V because it seems like a nice letter to use. And then, by another very surprising coincidence, we're going to call the log of the beta of STAT Q of STAT. So I'm just going to define these two symbols. And now let's see what happens when I plug in the logarithms of these betas. So this term, which computes the state-only message from the state action message, when I put it in log space, I get this equation. V of ST is equal to the log of the integral of the exponential of Q, right? Because the exponential of Q is beta STAT, and the expectation is taken under a uniform distribution, so that's multiplied by a constant. So this is the same thing expressed in log space. Now, what is this thing? Well, let's imagine that these Q values are really, really big. Then, when you exponentiate them, they get extremely big. So when you add together a bunch of numbers, let's say that they're all big, but some are bigger than others. So let me draw a little picture here. Let's say I have discrete actions, and maybe I have 3 actions. So they're big numbers like this. And then when I exponentiate them, the biggest one will get even bigger, and these will get bigger but not as much, right? So this one will be really, really huge. And now I'm going to sum them all together. This sum will be dominated by the biggest one. So when I then take the logarithm of that sum, that's going to come out to be quite similar to the logarithm of the biggest action, which is just the value of the q value of the biggest action. So as the q values get bigger, this log integral exponential approaches a max. In fact, you can actually show that if you put a multiplier in front of the q, if you make it exponential of like of like alpha times q, as alpha goes to infinity, this approaches a max. And for that reason, we sometimes call this log integral of exponentials a softmax. Not to be confused with a softmax loss that some of you might be familiar with in deep nets. It's called a softmax because as q's get big, it approaches a regular max, but for q values that are small, it's kind of a softened version of a max. So it's not quite a max because the non-maximal values still creep in there a little bit when the q values are small. So that's kind of interesting that we have something that's not quite a max, but it gets close to it for big q values. And of course, if it was a max, this v is equal to max q. That's a very familiar equation to us from dynamic programming. Now let's look at the other term, the one that allows us to back up a state message to get a state action message at the previous time step. If we write that in log space, it turns out to be equal to q is equal to r of s plus the log of the expectation of the exponential value of the next state. That makes sense because this first term, p of o given stat, that's just the exponential of r, so when you take the log of that, you just get r. Kind of looks reasonable, but a little weird. So we're used to seeing q is equal to r plus expectation of v, and now we have this weird log of expectation of exponential. That seems strange. But if we look at the form of the value iteration algorithm, we're getting pretty close already. So value iteration just has one step which sets q to r plus expectation of v s prime, and then sets v to be the max. Now we've replaced step 2 with the softmax, and step 1 with this weird thing. So what is that weird thing? What is that really doing? Well, first, if we have deterministic transitions, if our dynamics are not stochastic but deterministic, then this expectation happens to simplify very neatly, because if the transitions are deterministic, this expectation consists of exactly one term, and the log of an exponential just cancels. So for deterministic transitions, we do have the familiar form of the Q function. So for deterministic transitions, the only difference between this and regular RL is that we're using a soft max instead of a hard max. For stochastic transitions, we can think about what this formula is really saying a little bit. What it's saying is that if you have stochastic transitions, and some of them transition to good states, and some of them transition to bad states, because we're not taking the expectation, but instead this log integral exponential, this thing also looks a little bit like a soft max. So it says, if there's good outcomes and bad outcomes, just assume the good outcomes are going to happen, and the bad outcomes are less likely to happen. Which kind of makes sense if you think about the question that you're asking. You're asking the following inference question. Given that the monkey was doing the optimal thing, what were the states and actions that it saw? So it might have been doing the optimal thing because it took the right actions, or it might have been doing the optimal thing because it got lucky. So, given that the monkey won $1 million, what could have happened? Well, maybe the monkey won the lottery. That's not due to an action that the monkey actually took. It was just random chance, but it's an equally plausible explanation to why it got $1 million as the explanation that it, started a successful Silicon Valley startup or something. So the trouble with this probabilistic inference framework is that it doesn't really distinguish between intentional good outcomes and accidental good outcomes. And therefore, it makes a lot of sense that it would put an optimistic transition here to account for the fact that maybe you were optimal simply because you got lucky. But if we're reasoning about behavior, this is kind of a bad thing for us to do, because the monkey wasn't counting on winning the lottery. The monkey was trying to take optimal actions. So this is a little bit of a problem, and we'll actually see later on how we can deal with this problem. But before we do that, let's summarize the backward pass and talk about how we can recover a policy. So the backward pass involves computing the probability of O little t through capital T given a state and an action, which is the probability that we can be optimal at steps little t through capital T, given that we take action AT in state ST. And it's computed recursively from the end to the beginning, where you can do this in exponential space in terms of betas, as I showed before, or you can sort of recognize that the log of the beta function is Q function-like and do the same thing in terms of Q's and V's, in which case you get something that looks an awful lot like dynamic programming, where this first step consists of calculating the Q function, and the second step consists of taking a softmax to get the corresponding value function. So that's the backward pass. Now let's come back to this action prior for a second, because it turns out that we don't actually need to set it to be uniform. We can actually choose it to be whatever we want. Like maybe the monkey doesn't like taking big actions. Maybe it wants to take small actions because it's kind of lazy. We can encode that into the action prior. We can say the probability of big actions is lower and the probability of small actions is larger. Now, it turns out that this doesn't actually change our framework in any meaningful way. If we put in the action prior, then V is no longer the log of the integral of the exponential Q. It's now the log of the integral of the exponential Q plus log P. That's really the only change we have to make. So now, all we have to do is we have to take our original Q function, which I've written out here for the deterministic case, and introduce a different Q function, which I'm going to call Q tilde, which simply adds this log P A given S term to the reward. It's just a different symbol. I'm going to call it Q tilde. So Q tilde is just Q plus log P of A given S. And now V becomes just the log integral of the exponential of the Q tilde. So these are exactly the same. So what this suggests is that if we have a non-uniform action prior, we can just redefine our reward function. We can just say reward, it used to be reward, but now it's going to be reward plus this log P. And everything else stays the same, so we can take a problem with a non-uniform action prior and construct an equivalent problem with a uniform action prior, but a different reward function. Which suggests that in reality, we can just forget about that action prior, assume it's always uniform, and assume that any kind of actual action prior is just subsumed inside of the reward function. And that actually makes a lot of sense, because if the monkey doesn't want to take big actions, that probably means that its reward function gives it a negative reward for big actions. And the action prior is just uniform. Does anyone have any questions about this? Okay. So now let's talk about the second inference problem, which is perhaps the most important one, which is how do you actually get a policy out of this? So a policy in this framework is the probability of an action given a state and given O1 through capital T. So that's what is the probability of taking an action in a particular state if you are optimal. So again, we can do a little bit of probability theory and figure out what is P of A given S comma O1 through capital T. And we're going to call this pi because that's our policy. So first, we can recognize that the past doesn't matter because the action is conditionally independent. So A2, for example, is conditionally independent of S1 and therefore of O1 when conditioned on S2. So we can equivalently write this as P of AT given ST comma O T through capital T. So we can forget about the past. That keeps things a little simpler. And now we can write it out via the definition of conditional probability as P of AT ST given O1 T through capital T divided by P of ST given O T through capital T. So that's just from definition of conditional probability. And now what I'm going to do, I apologize for the alphabet soup here. Now what I'm going to do is I'm going to apply Bayes' rule to both the top and the bottom of this fraction. So all I did is for both the top and bottom, I applied Bayes' rule to put the optimality variables on the left side and the states and actions on the right side of the conditioning bar. So when I apply Bayes' rule, I get this division by P of O T through capital T on both the top and bottom, so that I can cancel out. And once I cancel that out, then I actually get something quite appealing. So I have two terms on the top and two terms on the bottom. The top term is the probability of O T through capital T given AT and ST. Does anyone know what that is? Have we seen that before? That's beta, exactly. So that's just beta, the state action backward message. And this thing at the bottom, that's the state-only backward message. So if I separate out the fractions, I get this thing, which is a ratio of backward messages, and this thing over here. So betas, I can put those in. So I get a ratio of betas, and this thing, this is just A given S. And remember that I assumed that A given S was uniform, so that I can just kill. That's a constant. So it turns out that the policy now is just the ratio of the state action backward message and the state backward message. So pi is beta ST divided by beta ST. Very simple. Which means that computing the backward messages is enough for me to figure out my policy. Question?
What happened to the PFS in the denominator?
So over here, this is P of AT comma ST divided by P of ST. So from the definition of conditional probability, it's just AT given ST. All right, so now let's bring back these value functions and Q functions and figure out what the policy ends up looking like in terms of Q and V. So our policy is the ratio of the backward messages, and if we substitute in V is equal to log beta ST and Q is equal to log beta STAT, then we get a very appealing form for our policy. Our policy is actually just the exponential of the Q value minus the value function, which is the exponential of the advantage function. That makes a lot of sense. That's like saying you're more likely to take actions with large advantage values and less likely to take actions with small advantage values. So actions that are better than average happen more often. Actions that are much worse than average happen a lot less often. So the policy has a very simple form in terms of the advantage function. So there are a few variants on this too. So just like we saw before with the value function, if we introduce a temperature, we can go from a soft max to a hard max. With the policy, we can also introduce a temperature. And if you introduce a temperature, meaning a multiplier in front of this thing, then as this temperature goes to 0, then the exponential of A basically ends up putting all the probability mass on the optimal action. So you can recover a deterministic optimal policy just by putting a multiplier in front of this thing. It has a very natural interpretation. Better actions are more probable. If you have two actions that are equally good, this policy will take those actions with equal probability, which is a little different from regular reinforcement learning, because regular reinforcement learning will have to break that tie, and will break that tie arbitrarily, whereas this thing will always assign them equal probability. And it's basically analogous to Boltzmann exploration. So if you remember back when we talked about Q learning, we talked about this thing called Boltzmann exploration, where we take actions with probability proportional to the exponential of their Q value, but back then that was kind of a heuristic. It didn't really have any like formal mathematical justification. But here we can see that it is actually the correct solution to solving a particular inference problem. And of course, as you decrease your temperature to 0, it approaches the optimal deterministic greedy policy. All right. So the last inference problem I'm going to talk about for this graphical model is the problem of forward messages. So forward messages are basically the opposite of backward messages. So backward messages tell you what's the probability of optimality given your state in action, the optimality in the future, and forward messages tell you what's the probability of a state given optimality in the past. And it turns out that if we put together forward and backward messages, we can figure out the probability of being in a particular state conditioned on the whole trajectory being optimal, which will be very useful later on for inverse RL. So the backward message is defined as alpha st is equal to p of st given O from 1 to t minus 1. And we'll see why it's t minus 1 later on when we combine this with backward messages. For now, it feels like a little bit of an arbitrary choice, but it's 1 through t minus 1. So alpha 1 is just the probability of being in an initial state. And we assume that we know this, so it's just some probability of starting in a particular state. And then the alphas can again be computed recursively, now forward in time. So it's going to, just like before, is going to consist of introducing variables and then integrating out those variables. So the variables we're going to introduce here are st minus 1 and at minus 1. So if we put in st minus 1 and at minus 1, and then factorize that distribution, we get the dynamics, st given st minus 1, at minus 1. We get the probability of taking the action at minus 1, given st minus 1, ot minus 1. and we get the probability of st minus 1 given O1 through t minus 2, which is just the previous the previous forward message. So we did, here I basically combined the two steps we had before. So first you introduce st minus 1 and at minus 1, and then you factorize that distribution by using the independence properties in the model. So this term is our transition probability, we know that. This term is our previous forward message. And that middle term is a little bit more complicated, but the middle term we can factorize like this. We can say that p of at minus 1 given st minus 1 ot minus 1, if we apply Bayes' rule, we get ot minus 1 given st minus 1 at minus 1, which is just our exponential reward, times at minus 1 given st minus 1, which is our action prior, which is uniform, divided by ot minus 1 given st minus 1. So if we plug this in here, we can ignore the proportionality constant and just normalize afterwards. We can calculate this entire quantity. So if we can compute these forward messages, then we can ask the question, well, what is the probability of a state given O1 through capital T, right? Because the forward message doesn't actually tell you what's the probability of landing in a state for an optimal trajectory. It tells you what's the probability of a state given that you are optimal up until that state. So if we actually want to know what's the probability of landing in a state along near optimal trajectories, then we have to do a little bit more work. So here's how we do that. P of st given O1 through capital T can be expressed by the definition of conditional probability as P of st comma O1 through capital T divided by P of O1 through capital T. And we're mostly going to deal with the numerator because the denominator, we can just normalize things afterwards and ignore it. So we'll just deal with the numerator. So for the numerator, the property that we're going to use to take care of it is this conditional independence. Because remember that if you know S2, for example, then O2 is conditionally independent of S1. So given a state, the optimality variable of that state is conditionally independent of previous states. So we can exploit this and factorize this distribution here to be the probability of the optimality variables in the future, t through capital T, given st, times the probability of st comma O1 through t minus 1. And the second term, so the first term is just the beta, and the second term we can deal with like this. So we'll ignore the proportionality constant, so we'll write this as proportional to beta times st given O1 through t minus 1 times p of O1 through t minus 1. So I've just factorized this by the chain rule. And then the second thing is just alpha. And the last thing doesn't depend on st, so if I'm going to normalize things afterwards, I can just ignore it, because up to a constant, the probabilities will be equal. So that means that if I want to know the probability of being in some state st in a distribution over near optimal trajectories, all I have to do is multiply together the forward message and the backward message, and then renormalize. So those of you that are familiar with common smoothing and HMMs will recognize this. This should be actually quite familiar. So that means that our probability is just the product of the backward and forward messages.
What's P O T minus 1 given S minus 1?
P of OT minus 1. This thing. The denominator. This thing?
About 9.
This thing.
Yeah.
I see. This thing we actually don't have to worry about, because if it appears in the denominator, we can just renormalize things afterwards. So you can figure out what it is, and you can crunch through all the same algebra, but it turns out not to matter. All right. Let's analyze this thing a little bit more. The beta times alpha. What is this really saying? We can get a pretty nice kind of visual intuition for what the product of the backward and forward messages means, like this. Let's say that we're trying to reach some destination, and we need to start in this state. So the optimal path, of course, is a straight line. The backward message tells us, roughly speaking, what are the states from which we'll be happy to kind of efficiently reach this target. So this kind of backward cone this is the set of states from which we will be able to reach our goal. So if you say your reward is like +1 if you reach it and 0 otherwise, then your backward messages will look like a cone emanating backwards from the goal state. Your forward messages will look like a cone emanating forward from your initial state, because the forward messages tell you what are states that you can reach with high probability given optimality in the past. So these are, the blue kind of denotes the states that you could reach with reasonable rewards starting from the initial state. When you multiply them together, you basically take their intersection. So when you take their intersection, then you get these state marginals, which, if your goal is to reach this location, you'd expect them to grow in variance as you approach the midpoint and then shrink in variance because you need to actually arrive at this destination, so you need to lower your variance in the second half. So we'd expect that for, yeah, question?
No. Oh, I have a question.
Yeah, go ahead.
Here it looks like we're multiplying effectively this is like Dijkstra almost, where you're, instead of taking the distance from the start to the end, you're multiplying instead of adding. Is there like a log difference between the two?
Oh, yeah, so if you want to know why it's multiplying instead of adding, just remember this is all in exponential space. So if you take the log of this, then you get addition. So all these terms, if you want to like imagine what units they're in units of exponential reward. So if you take their logarithms, then you get addition.
Okay, so this is then almost like Dijkstra.
Yes, yeah. So in that sense, yes. So in the sense that the probabilities of seeing these things depend on sums of rewards. And sums of rewards in log space correspond to products of exponential rewards in exponential space. So this can be taken to be, in some sense, our first prediction. We would predict that if someone is trying to reach a location in space, you'd expect their variance of their states to increase as they leave the initial state up until the midpoint, and then decrease as they approach the target. And it turns out that actually, if we study movement of humans performing reaching behaviors and plot the variance in the location of their endpoint, so here a person is asked to perform a reaching behavior with a stick. This is from a paper by Lee and Todorov. It turns out that actually the position of their endpoint exhibits the same kind of variance structure, that obviously you have low variance when you start because you start in the same place. Your variance increases as you leave the initial state, and then decreases again as you approach the target, following a pattern very similar to what you'd expect from multiplying the backward and forward messages. Okay, so question, yes?
What's a good way to think about that? X-axis, because I don't want to just think about x distance or Euclidean distance. It's through the state space, right?
Yeah, so you can pretend here that the x-axis is sort of a cartoony visualization of all of state space. So this is not a space-time plot. This is like everything here is space. All right, let's continue. So to summarize, I described a probabilistic graphical model for optimal control, which is basically your MDP augmented with these optimality variables. I described how control ends up corresponding to probabilistic inference, which is very similar to what you do for HMMs or Kalman filters. And how it's also very similar to dynamic programming. If you take the logarithms of your backward messages, you get things that look like value functions and Q functions, but now they're softened in some sense. So now, in the next part of the lecture, this is going to get a little bit more advanced mathematically. I want to deal a little bit with that with that optimism problem that I mentioned before. So if you remember, we worked out that if you take the log of beta, you get V. If you take the log of beta ST8, you get Q. But the corresponding Q looks kind of weird. It has this optimism issue where you're actually saying that you're going to set the Q value to be the soft max of the next value, not the expected value of the next value. And that's maybe not so good, yes?
Isn't that kind of what we do in Q-learning anyways, though?
So the question was, isn't this kind of what we do in Q-learning anyways? In Q-learning, you choose the max of the Q value at the next state with respect to the action. But you don't choose the max with respect to the state. And that's a very important distinction because the action is something you get to choose. The state is chosen for you by nature. So maybe now we can ask the following question. Why did this happen? Why did we get this optimism problem when we used probabilistic inference to figure out our Q function? Well, remember that our inference problem is to figure out the probability of states and actions given that we observed the agent being optimal. Being optimal specifically means getting high reward. So what's the probability of a sequence of states and actions if we know the agent got high reward? And as I said before, the agent might have gotten high reward because they did the right thing, or they might have gotten high reward because they got lucky, because they won the lottery. And if you know they got high reward, then of course you should figure out the right actions that they took. You should, when you marginalize on condition, you get AT given ST, comma, O1 through capital T, then better actions should be more likely, because if they got high reward, they probably took good actions. But, so this basically amounts to saying, given that you obtained high reward, what was your action probability? But you can also marginalize on condition for the state transitions. You can write down, well, what is P of ST plus 1 given STAT, comma, O1 through capital T? So that's saying, if I know you got high reward, what do I believe about your state transitions? And this is not equal to the dynamics that actually govern the system. So perhaps the dynamics that govern the system is that you have a 1 in a million chance of winning the lottery. But if you know that you got like 10 million bucks, then your posterior about what your probability of winning the lottery was is probably higher. So if O here denotes that you got millions of dollars, and the state includes an entry for did you win the lottery, then P of you won the lottery given this stuff is larger than your prior P of winning the lottery given this stuff. So that's like saying, given that you obtained high reward, what was your transition probability? And the answer is it was not the same as your prior transition probability. This is reasonable if we're answering inference questions, but it's not really reasonable if we're thinking about optimal behavior. Because we don't want to figure out how likely is it that the monkey won the lottery. We want to figure out how likely is it to take different actions, given that it's trying to optimize some goal. The monkey didn't know that it was going to win the lottery when it was trying to optimize that goal. So we need to address this problem somehow. We need to figure out how we can basically do this part without doing this part. So we want this, but we don't want this. So what we really want to answer is the following question. Given that you obtained high reward, what was your action probability, given that your transition probability did not change? So this thing is not going to change, but we still want to know what was your action probability given that you got high reward. This turns out to be a bit trickier to do, but we can use some of the tools from last week to make this possible. So what we're going to do is we're going to find another distribution, which I'm going to call little q, which is going to be close to P of S1 through capital T, A1 through capital T, given O1 through capital T, but has the same dynamics as the prior. So I'm going to force this q to have P of ST plus 1 given STAT as its dynamics, but otherwise it can have a different policy. So where have we seen this before? Well, if we set x to be O1 through capital T and z to be the trajectory, then this looks an awful lot like the variational inference stuff that we discussed last week, because in variational inference, our goal was to find q of z to approximate p of z given x, and now we're going to find q of tau to approximate p of tau given O. So let's try variational inference. Let's see what variational inference gets us. So we're going to choose our distribution little q, and we're going to choose it as following. We're going to set the initial state distribution, P of S1, to be exactly the same as the initial state distribution in P. So Q of S1 is equal to P of S1. We're going to set our transition probabilities to be the same as P. So Q of ST plus 1 given STAT is going to be set to P of ST plus 1 given STAT. In variational inference, this would be a very weird choice, but we have a good reason for making that choice, because we want to make sure that the dynamics do not change. And then we're going to have this Q of ATST. That's the only thing that's going to change. So the same dynamics and the same initial state as P, and the only new thing is our action conditional. So our model P looks like this. It has states, actions, and optimality variables, and the optimality variables are observed. So it has P of S1, it has P of ST plus 1 given STAT, and it has P of OT given STAT. Our approximation Q, just like in variational inference, it doesn't have the observed variables anymore. It's only over the latent variables. It's going to have P of S1, just like up here. It's going to have P of ST plus 1 given ST-AT, just like here. And then it's going to have Q of AT-ST, and that's the new thing. So it doesn't have P of OT given ST because O is observed, so that doesn't appear here. But now it has this Q of AT given ST. So what we're trying to do is we're trying to approximate this distribution with this distribution, which is like saying, find me the closest distribution that looks like the one where the optimality was satisfied, but where the dynamics did not change from the true dynamics of the system, while the policy, Q of AT given ST, did change. So in variational inference, we had X's and Z's. So our X's are basically O1 through capital T, and our Z's are all the states and actions. So this thing basically plays the role of Z given X, and this plays the role of Q of Z. So now what we can do is we can plug this into to our variational bound, and we can figure out a bound on the likelihood. So the likelihood that we're concerned with is, of course, the likelihood of our optimality variables, because that's our evidence. And we know that it's bounded by the expectation with respect to Z under Q of log P of X comma Z minus log Q of Z. This is just from last week. So now let's plug in our choice of X and Z. So our X's are the optimality variables. Our Z's are the states and actions. We plug them in using our definition of Q. And we get the log probability of all of the optimality variables is greater than or equal to the expectation under the states and actions that we get from Q of, now I'm going to factorize the P. So P can be factorized as log P of S1 plus the sum of the transition probabilities plus the sum of the optimality variable probabilities. So this part is just the log of the P. And then you have to subtract log Q, which comes from the entropy. So there again, I'm going to factorize the Q. That gives me a minus log P of S1 from my definition of Q, a minus sum of log probabilities with transitions, and then a minus sum of the action probabilities. And now, because of how I chose Q, of course, the initial states cancel out and the transitions cancel out. So all I'm left with is the expectation under the distribution over states and actions in Q of the sum of the rewards minus the log probabilities of the actions given the states. So because of how I chose the dynamics and the initial state, everything actually simplified quite neatly into this form. And of course, this last term is still the entropy. It's the entropy of the action distribution. So I can equivalently write this as the expectation of the reward minus the entropy. And this now looks an awful lot like a policy learning objective. Remember, a policy learning objective is the expectation of the reward. Now I just have the expectation of the reward minus the entropy. Actually, this should be plus the entropy. There's a typo here. There should be a plus. So this just says that now, if you want to find the Q in this framework, all you have to do is maximize the reward and maximize the entropy. Whereas before, in regular RL, you were just maximizing the reward. Which is quite neat. We went through quite a lot of mathematical derivation, and we arrived at something that looks very similar to what we already knew, which is maximizing the reward, except that now we also have to maximize the entropy. So now let's talk about how we actually optimize the variational lower bound. So from the previous slide, our bound is the expectation under Q of the reward plus the entropy. Sorry about the typo again. And we can do this in a number of ways. Like one of the ways we could do it is we could actually just take this expression up here and use policy gradient to compute its derivative. It's kind of discarding everything we learned about in this lecture, but why not? Like it's an expression, we can compute its gradient, policy gradient, it'll all actually work. We can still derive a dynamic programming version, just like we did earlier. The dynamic programming version actually looks even more like regular dynamic programming. So let's go through that, but remember that you can also do policy gradient here if you want. So the dynamic programming version, just like always, we're going to start at the base case, solve for a Q of A capital T given S capital T. So Q of A capital T given S capital T, it only affects one of the terms in the sum, the last one. So that's just given by the argmax of the expectation under the state marginal, of the expectation under Q of AT given ST of the reward minus its entropy. And equivalently, you can write that as the reward minus log little q. Sorry, this should be, again, plus the entropy. But the minus little q is correct. So anytime you see an expression of that form, this is just kind of a general thing in machine learning. Anytime you see an expression that looks like expectation under some distribution q of x of r of x minus log q of x, the maximum of this is always 1 over z times e to the r of x. And you can, if you want to convince yourself of this, you can take this quantity, compute its derivative with respect to q, and set that to 0. It always comes out to be the exponential of the thing over here. So this is just a good kind of identity to remember, that the optimum is always going to be the exponential of the thing over here if you're subtracting the log probability. So this is minimized when q of AT given ST is proportional to the exponential of r. And in particular, q of AT given ST is equal to the exponential of r divided by the integral of the exponential of r with respect to the action. So this is the normalization constant. You get the normalization constant by just integrating the thing over the whole domain, which we can write to be equal to the q function minus the value function, right? Because the q function at the very last time step is just the reward because there's no next step. So this thing in the exponent at the top, that's just the q value. And the bottom, this is the exponential of the log integral exp, because it's the integral exp. And that's just how we defined the value function before. So if the value function is a softmax, then the exponential of the value function is exactly the denominator here. So at the last time step in the base case, this is equal to the exponential of q minus v. I mean, in some ways, this is kind of a silly identity because that's just how we define v. We define v to be the integral of q. So of course, it's q minus v. So what that means is that if we actually plug in this equation for q of AT minus, for q of AT given ST, if we plug that into this objective at the bottom, then it becomes equal to the expectation of the value function, right? Because this thing has two terms. It has a reward term and a value term. Reward minus reward is 0, so that just leaves the value term, which means that if you choose the optimal q of A capital T given S capital T, then the only thing that remains here is the value function. And that's important because that's going to inform how we do the recursive case. So let's move on to the recursive case. In the recursive case, we had this from our base case. We had the only thing that was left over in the objective was the expectation of the value function. And now q of AT given ST is going to be the argmax of the expectation under the state distribution, of the expectation under the action distribution, of the reward at that time step, plus the expectation of the value at the next time step under the transition dynamics, plus the entropy. So again, this is a little typo. It should be plus the entropy. And now we're going to define our q function in the usual way. So unlike before when we had the optimism, now we're going to choose to define our q function as reward plus expected next value. And of course, we see that this expected next value lines up very nicely with what we have in our objective here, because this is the expectation of the next value. I mean, it's really the expectation of the next terms in the objective of this stuff, but we previously proved that this stuff is just the expectation of value, so that's where we get that. So that's just the regular Bellman backup. It's not the optimistic Bellman backup anymore. So when we then plug this in, we get the reward plus the expected value becomes the q function, and here we have plus the entropy, which becomes minus the log q. So this form of writing it out looks exactly like the thing we had in the last slide, except that now instead of r, you have q. And just like on the last slide, that means that the optimal action distribution is proportional to the exponential q values. Before it was the exponential reward values, now it's the exponential q values. And just like before, the normalizer is the value function, which means that q is again equal to, which means that little q of AT given ST is again equal to the exponential of big Q minus big V. And the objective again becomes V of ST. So in the recursive case, we also get the conclusion that the policy is equal to the difference between the Q value and the value function exponentiated. And the backup is given by the regular Bellman backup, which is not optimistic anymore. So the summary of the variational version of the backward pass is the following. The recursion looks at this point almost identical to regular dynamic programming. The Q function is backed up in the regular way, and the value function uses the softmax. So the regular value iteration algorithm differs from this only in the sense that it has a hard max instead of a softmax. And this can be viewed as soft value iteration, where all you do is you replace the hard max with a softmax. So to summarize, we had our original model, which is S1 through capital T, A1 through capital T, given the optimality variables. We approximated with a variational distribution, where we chose the transition probabilities to equal the prior transition probabilities and the initial state probabilities to equal the prior initial state probabilities. And then when we went through the dynamic programming equations, we figured out that all we have to do is solve for our value function via the softmax and solve for our Q function using the regular Bellman backup. For more details on this, you can read this tutorial if you want to learn more about the details of the variational inference procedure, if you want to get a little more in-depth on how the optimization works out and so forth. There are also a few variants of this technique that are worth keeping in mind. So first, it's very easy to introduce a discount into this framework. The justification for introducing a discount factor is basically the one that we covered before, that if you imagine the discount factor as simply changing your transition probabilities, you're allowed to choose any transition probabilities you want, so it's perfectly all right to put a gamma in front of the expectation. It's also very common in the literature to see this framework used with an explicit temperature. An explicit temperature means that inside the softmax, you put a 1 over alpha in front of the Q and then multiply the alpha back in on the outside. So here, as the alpha goes to 0, the softmax approaches the hard max, and that lets you interpolate between the soft framework and the conventional framework of regular reinforcement learning, which is a limiting case of this as you take alpha to 0. So if you see a temperature in front of this thing, that just means you're doing this. Okay, does anyone have any questions? Yeah, we're not going to have a break because we have 5 minutes left. Does anyone have any questions about this derivation, about the variational inference derivation for approximate optimality?
I'm curious
Yeah.
about what this kind of method that it works in the previous IELTS algorithms, like
Yeah. So the question is, can this kind of method work in the previously proposed algorithms? Yes, and that's actually what I'm going to cover in the last 5 minutes. So that's what I'm going to talk about next.
So you mean we can replace the V as
Yeah, that's coming right up. So let's, yeah, this is the right slide for that. I think it's actually going to be very straightforward. So one of the things you can do with this framework is you can actually use soft optimality with your favorite reinforcement learning algorithms. And I'm going to tell you about this in the context of Q-learning and also policy gradient. So for Q-learning, it's very simple. Standard Q-learning just consists of this update. You update the parameters in your Q function by the gradient of the Q value times the Bellman error. And the Bellman error is just the target value minus the Q. Or you can make this a minus sign and flip the order of these equivalently. So the target value in Q-learning is given by the max over the next Q function, right? In soft Q-learning, this equation is exactly the same. The only thing you change is the target value. So instead of having the target value be a hard max, you change it to be a soft max. And there's one small change you have to do, which is that if you want to follow the framework of approximate inference, then once you're done solving for the Q function, you should choose actions according to the exponential of the Q value minus the value function. So in regular Q-learning, you choose the action by taking the max over the argmax. Here, you have to choose the actions by doing the soft argmax, which is the exponential of Q minus V. That's right, yeah, which means they need to be sampled from this distribution. Because this is no longer trying to find you a deterministic optimal policy, it's trying to find you a stochastic optimal policy, where the stochastic optimal policy is given by this bottom equation. So this gets you soft Q-learning, which is essentially Q-learning with this probabilistic inference framework. The resulting algorithm is basically exactly the same as regular Q-learning. The only difference, you now do a softmax, and the policy that comes out, it's still an off-policy algorithm, so you can explore using whatever policy you want, but when you're done learning, then the policy that you should run is this exponential of the advantage. And that's it. That's all you have to do to turn this into Q-learning. If you want to do policy gradient, it's actually even easier. So for policy gradient, you can directly optimize the variational lower bound. So for policy gradient, you just directly maximize the expected reward plus the entropy. And for most popular policy classes, like softmaxes over discrete actions or Gaussians, the entropy has a closed form expression. So you can just write it down and compute its derivative. Or it actually turns out that you actually get the right derivative if you just subtract log pi from r. So you can also do that. You can just change your r's to be r minus log pi, plug that into your favorite policy gradient algorithm, and you'll also actually get the right answer. You get slightly lower variance if you compute the derivative of the entropy analytically, but simply subtracting log pi from your rewards actually works fine. So that's your policy entropy, and that's the only change. So the intuition here is that your policy ends up being proportional to the exponential q when the policy minimizes the KL divergence between pi and the normalized distribution for exponential q. So that's how you can do policy gradient. Again, very, very simple. I'll skip the rest of this part. And what I wanted to talk about briefly in the remainder are some of the benefits of doing this in a reinforcement learning framework. So one of the big benefits, which we'll see mostly on Friday, is that this allows us to analyze near-optimal behavior of other agents and recover their goals and rewards. But even if you're mainly concerned with doing forward reinforcement learning, the reinforcement learning algorithms that are derived from soft optimality can often have a number of benefits. So one of the things that they can do is they can improve exploration and prevent entropy collapse. So this is especially a big issue for policy gradient algorithms. Some of you might have noticed this actually in homework too, but if you play around with policy gradient algorithms, if you look at what happens to the variance of a Gaussian policy, let's say in the first few iterations of learning, the variance of the Gaussian policy tends to drop very rapidly because locally, the policy always gets better if it reduces variance if there's some kind of penalty on executing large actions. So it's very tempted to reduce variance early on, which of course stifles exploration and might cause it to converge to a suboptimal solution. So the entropy term that ends up getting added to the policy gradient objective mitigates this to a large degree and maintains a high degree of exploration. Another perhaps less obvious benefit of this kind of framework is that it can be much easier to fine-tune the policies that are trained with maximum entropy to new tasks. And I'll show an example of this actually on the next slide. This method provides a very principled approach to break ties because equally good actions get equal probability. And you can actually also get better robustness because your policy is essentially trained with this injected noise. So if you can maximize reward while having high entropy, then that means that you can deal with unexpected events. You can deal with unexpected noise being injected into the policy. All right, I'll skip the rest of these, and what I want to do is I want to show some of the examples for fine-tuning. So I'll go through this a bit more quickly. So what I'm going to show here are some videos for a soft Q-learning algorithm. So this is basically a deep learning version of that soft Q-learning method that I showed a few slides ago. And what we're going to do is we're going to use soft Q-learning to train a policy to do an underspecified task. How many of you remember the ant from homework 1, this four-legged thingy? Okay, most of you remember it. Okay, the next video is going to be a little creepy. The left side is showing a baseline, so don't worry about this, but pay attention to the right window. And what this is going to show is soft Q-learning optimizing a reward function for the ant that rewards it for running in any direction. So the reward function is just the magnitude of the velocity. Now, if you give that reward function to a regular RL algorithm, what it will do is it will maximize velocity in some arbitrary way. So maybe it'll run this way. With soft Q-learning, because it has to maximize entropy, it has to actually learn to run in all possible ways. So the optimal soft Q-learning solution is to run fast in all possible directions. And that's actually what you see there on the right. You see this creepy ant thingy just running in all possible directions. And now you might say, well, why is this useful? Why do we want ant to run in different directions? Well, if you use this as an initialization, and then you put the ant in a new environment like this hallway, it can then fine-tune to the particular hallway much more quickly because it already learned to run in all directions. Whereas if you use regular RL to retrain, then it will pick some arbitrary direction, which may not be the same as the direction in the hallway. So in the video on the right, what you're seeing is over here, this is fine-tuning on the hallway when initialized with soft Q learning. This is fine-tuning from scratch, and this is fine-tuning initialized with deterministic RL, which is actually the DDPG algorithm that we covered before. And what you're going to see here is as learning progresses, so the epoch number is here at the top, the one that's initialized with soft Q learning learns to run further much more quickly because it already has the ability to run in all different directions inside that Q function and only has to figure out which direction is correct. Whereas the deterministic initialization has to essentially unlearn running in the wrong direction and then relearn running in the right direction. So this is one of the benefits of incorporating soft optimality. Okay, if you want to learn more about this, suggested readings. So there's quite a few of them, but I'll walk you through some of the broad categories. So these first two, these are by Emanuel Todorov, who developed a framework called linearly solvable Markov decision processes, which are a variant of soft optimality that actually marginalizes out the actions and only operates on states. Bert Kaplan also has some really interesting work that combines probabilistic graphical models and control in a framework very similar to this, and also some extensions to continuous time. So if you're really into partial differential equations, Bert Kaplan's work will teach you a little bit about how to do this in continuous time. It's rather complicated, and it actually uses a bunch of theorems from quantum mechanics, so that's kind of cool. If you want to know about inverse reinforcement learning, Brian Ziebart has done a lot of work that connects soft optimality to inverse reinforcement learning, and we'll cover that on Friday. This paper by Rawlik Toussaint et al. Covers using soft optimality in a kind of dynamic programming Q iteration style algorithm. And then these last, these four papers, these are more modern, deep reinforcement learning papers that make use of soft optimality. And the and thing that I showed is actually from the 2017 paper by Harnoy et al. And then this last one, this is a tutorial that describes the variational inference framework. So if you want to learn more about any of these topics, do check this out. And then on Friday, we'll talk about inverse RL, inferring rewards from demonstrations. So I'll see you all then.
Quick questions. When you say policy gradient, just minus the log probability from the reward, right?
Yes.
So if the probability is really